Hi, welcome back. So we have now we are looking into alternate current. Alternate current is our current that varies, and it also goes from positive to negative and vice versa. So we saw how alternate current actually, when it flows through a resistor, the way it flows, and basically the mathematics that we use to calculate current and voltage, etc., are not very different from what we actually do it in DC, okay, direct current. However, we have also seen that we had to actually introduce a new concept called as RMS current or RMS voltage, which is an equivalent current of DC, which heats up or which consumes the same amount of power. Because in this case, the we can't work with the averages because average tends to be zero. So now what we are going to do is to figure out what happens if an AC current flows through an inductor, purely. See, no circuit is actually a pure inductor, because an inductor is made by wiring, winding the wire, and when you wind the wire also has resistance. So the all inductors are also having some resistance. But however, in ideal scenario, we will neglect that and we say it's a pure inductor, means there is no resistance. Okay. So what happens in that case? We will see. Okay. So here is an inductor. Okay. So we will say that has some voltage V. V is a V of t. Okay, in the sense that it is a function of time, and current that flows through here is I of t. Lowercase letters are basically uh, variable variables, and this has an inductor. Let us inductance. Let us say L. So it's a self inductance. Okay, L. So now we are going to basically write down even here Kirchhoff's voltage law. Kirchhoff's voltage law is basically saying that the sum of all the voltage you take across in a loop basically is equal to 0. So I will go from this side. V. So what is V? V is equal to, we'll just write V first. V is equal to Vm sin omega. Okay. So now we will write the Kirchhoff's by KVL. Okay. Kirchhoff's voltage law. We can write that V minus, when you go this way, okay, the voltage across an inductor is L into di by dt, that we had actually derived in the last section in the electromagnetic inductance, in the induction. There we have derived it. Okay, L into di by dt. So the negative sign is basically it is in the opposite direction, is equal to 0. Okay, so we can write this as di by dt is equal to V by uh, V by L. Now, what we will do is we will basically write down what V is, okay, which is Vm sin omega t divided by L. So this one actually, if you see, I'm going to basically multiply both sides by dt. Okay, this is no, this is not a very correct way of saying it, but that is how you generally solve the differential equations. Di by dt into dt is equal to Vm sin omega t by L dt. This is that separation of the variables, separating variables kind of a method of differential equation solving. Okay, so you will come across that in the mathematics. I'll write this as di is equal, dt will cancel. I'll say that Vm by L, which is constant, I'll say sine omega t dt. So we are now basically going to integrate both sides to get back I. Okay, our idea is to find out what is I. Given a v, what is I? That is what we are trying to find out. Okay, so I'll integrate both sides. This being a constant, I'll keep it out. So when you integrate di with respect to I, we get it actually I. Integration of dx with respect to x is x. So Vm by L. So sin omega t, if you integrate, you will get minus cos omega t by omega plus c. So we're going to use a certain argument. We're saying that when there is no voltage, there will be no current. Okay? And there is zero voltage. So by taking that into consideration, we can actually substitute that and compute and say C is actually zero. Okay. So C we want to say that is and it also, we know that it moves between positive and negative and does not have a certain bias. Some constant is not added to it. Okay, always. So we'll say that C actually tends to 0 when you compute that. So I'm not going to do a very elaborate discussion on that, but when that happens, we can write it as I is equal to Vm by omega L, okay, into minus cos omega t. This is our I. So however, we can write cos omega t in the cos theta is equal to sin pi by 2 minus theta. Then anytime cos theta becomes sin 90 minus theta, they are same. Sin 30 and cos 60 are same, for example. Okay, so we can say Vm divided by omega L into minus of sin pi by 2 minus omega t. We can write that. R sin minus theta is equal to minus sin theta. Okay, and R minus sin theta is equal to sin minus theta. We can write that as sin omega t minus pi by 2. So this minus I take it inside. So this is I. So let's see. This is I. And this is B. So we are going to basically also write this as I is equal to I max into sin omega t minus pi by 2. Hence, we can actually say that I max simply is equal to V max by omega L. If you remember, in the case of a resistor, we got I max as V max by R. That means denominator was a kind of a resistance. Okay. So current is equal to voltage by resistance was very nicely Ohm's law. So we accepted that. Here actually the denominator is not a resistance. So we call this denominator as similar to resistance but inductive in nature. Okay, so we call that as reactance. So this is called as reactance. So we call this as reactance. In this case, it is a inductive reactance and it is represented by XL. X is a reactance. So L is an inductive reactance. So we can say XL actually equal to omega L. So what does it mean? We'll see. Okay. So L is the inductance. Okay, L is nothing but the self inductance, which is not like, which does not have the units of a resistance. Okay, whereas this actually has the units of a resistance, okay, omega L, because you can see omega L is same as Vm by Im. So voltage by current is the units of a resistance, but this is a very special kind of resistance, and it is called inductance, and it's called inductive reactance. And in the case of a resistance, if we had a resistance here, so whatever may be the scenario, the value of the resistance remains same as long as you keep the temperature same. Whereas in this case, you can see the reactance does not depend only on the inductance. The reactance depends also on the omega. Omega is nothing but, what is omega? Omega is 2 pi into f, or 2 pi by t. Okay. F is the frequency. Let us say if you have your at home you have an AC which is 50 hertz, then this is nothing but 100 pi, which is like 314 point something, is basically the value of the omega. Okay, into the some millihenries inductor. So you will get the reactance, which is ohms. Reactance will be in ohms. This is ohms. Ohms. So reactance of an inductor depends on the frequency, okay, in the sense that instead of everything else being same, you have the same 220 volt supply, everything being same. If you just change the frequency of the circuit, that means the variation of alternate waves, if it changes, then the reactance changes. So the reactance constitutes basically, what is the reactance doing? If there is a reactance is higher, then the current is lower because it works like a resistance. So in an AC circuit, if you take, okay, if this was not an AC circuit, think about it. If this was not an AC circuit, then if you had a DC here, there is absolutely no opposition, because the inductance gives opposition to the current only when there is a change in current, because the back EMF that gets basically induced into this is proportional to the rate of change of flux. Okay, if there is a constant current flowing through this, then this whole thing behaves like a zero resistance, because omega being zero, f being zero. So that means that very high current will flow if it is a DC. But as you increase the frequency, the reactance will keep on increasing, that XL value, and current will keep coming down. So for very high frequencies, this will actually become very high reactance, and current keeps on reducing. So it opposes basically change in current. Okay, it opposes change in current. Resistance opposes current itself, the flow of current, whereas inductance opposes change in current. That is, whenever the current is changing, if it changes too often or is changed at a higher rate, then its opposition will be more. Okay, that is what is a reactance. So that's what we have clearly proved it here. Okay, so what we saw is we came to understand a new word called as reactance, and it is similar to resistance. The reactance is, and only difference is in terms of unit, it is similar to resistance. The difference is that it depends on the frequency. Okay, and we proved it that XL is equal to omega L, and we also proved what is the value of I. Okay, I, so V is equal to Vm sin omega t. Okay, and I is equal to, we will write it here clearly. I will erase the remaining. So I is equal to Im sin omega t minus pi by 2. So till now we were not actually giving much importance to this minus pi by 2. Okay. So we are going to now attack that part. What is the meaning of minus pi by 2? Okay. So that we will come to know when we look at the phasor diagram. So let's now, what our new tool called phasor diagram, we're going to use it now. So if you look at AC voltage applied to the inductor, how does the phasor diagram look like? First thing I'm going to write here is um, the voltage. Okay, the voltage is varying like this, and this is time, and this is voltage, and this maximum value here, I'm going to write it as Vm, and it is running at frequency, angular frequency omega. Okay. We'll do is at that level height, same height, I'm going to draw two lines here, and I'm going to draw actually a circle whose radius is actually Vm. Okay. And we're going to draw a line here which actually demonstrates the phasor. This represents the phasor of voltage. This is our voltage, just V. So saying that V is equal to Vm sin omega t is represented by just this V, because this is going to vary like this, and this is our uh, angle that keeps changing. Okay, and when the angle changes, it produces this wave. Okay, because this height is what we are actually measuring. This is height is our V. This height is our V, and this is our Vm. So this V is nothing but this height. Now what happens is that if you actually look at the current, so let's now draw the current. How is the current looking at? I is equal to Im sin omega t minus pi by 2. So we have drawn here V, which is Vm sin omega t. And now we are going to write the other one, which is I. Look at how I looks like. So this height, I agree that it is nothing but this height is Im. This is the height Im. Okay, and since if it was just sin omega t, okay, then it would have actually varied along with this. It was fitting into the, it would have fit into that curve. But now because it is minus pi by 2, which actually means, what is the meaning of that? That means that if you actually shift it, if you shift it left, that is minus means left, okay, by pi by 2, it will align with the other one. So you will take this, just move it like this to the left by pi by 2. See, this is 90 degree or pi by 2. This is 180. This is 270. This is 360 or 2 pi. So this is pi by 2. If you move the second one left to pi by 2, it actually aligns with the original. So that is the mean of this. Okay, that means that if this is negative here, it means basically I is lagging V. He says that I actually is lagging V by an angle pi by 2. So that is the meaning of this. Now if you plot this actually as a phasor, if you want to represent it, how does it look like? So again we draw a line here, and we draw a circle of that Im size, okay. And then we are going to draw the vector here, which is lagging by 90 degree. Okay, so if it is actually rotating, always rotation is anti-clockwise. Okay, take it like that. If this is rotating at anti-clockwise direction, and this also rotating at anti-clockwise direction, like this, and the angle between them is 90 degree. So it is lagging. That means the place wherever this is, to that place, for it to come, it takes 90 degrees moment. So it is behind the voltage by 90 degrees. So if you ask in an inductor, okay, in an inductor, always current lags voltage by 90 degrees. You can say so, or you can even say voltage leads current by 90 degrees. pi by 2. So voltage here is leading, that is the front. Okay. Or we can say current actually lags. So both are equally valid statements. Okay. So this is the phasor diagram. Whenever we write a phasor diagram of an inductor, pure inductor, if we write a voltage like this is our voltage, current will always be written 90-degree back side. This always rotates in this direction. So 90-degree, this will be current. There will always be a 90-degree between current and voltage, and voltage leads. This is the phasor diagram. So why is that required phasor diagram for us? When we do the analysis of the circuits, you will realize how easy circuit analysis will become if you use phasor diagrams. Okay, this is our basic understanding of voltage and current relationship in a pure inductor circuit. So now what we will do is what happens to the power. Okay, let's look at the power. So power consumed by an inductor. So what I'm going to do is we are going to write again. This is our Vm sin omega t. Okay, this is our V. We call this as this is V. Okay. So as written, and we'll also write I. We saw that I is actually lagging. Okay, this is our I, which is Im sin omega t minus pi by 2. Okay, these two are there. Now what we are going to do is to multiply these two. Okay. So we can multiply, like for example, at every point you can take and multiply. Every point you can take and multiply and draw it. Okay. Or you can do mathematically also do that. Okay. So we will say power is equal to V into I, which is Vm Im sin omega t into sin omega t minus pi by 2. Okay, so sin omega t minus pi by 2 can be actually written a little differently. How can we write? So we write it as cos, okay, Vm Im sin omega t into minus cos omega t. Okay. Now we are going to again. This is exactly we did in the opposite way. Earlier we got minus cos omega t and we wrote it like this as sin omega t minus 2 by 2. So we can write this as again, okay, minus, we say minus into Vm Im by 2. I will write, okay, and I will also write into 2. I'm just going to do 2 into 2 and also 2 like here, and this math I have written here. Here I will write sin omega t into cos omega t. There's a lot of simple trigonometry here. Okay, so here you can go and say that I'm going to write again here minus. This is Vm by, I will write it as root 2 into Im by root 2, because root 2 into root 2 is 2. Okay, and 2 sin omega t can be written as sin. See, 2 sin theta cos theta is sin 2 theta, sin 2 omega t. This is the power. At any instant, this is how you calculate the power. Okay, so and when you want to basically draw that power picture of that, how does it look like? Okay, let's see how does it look like. So let's look at how the power looks like. Okay, when we as a diagram, if you plot it, how it looks like. So power looks like this. So it is a multiplication of V and I. So you know that when you multiply V and I, if this is actually minus sine 2 omega t, you can see. Sine 2 omega t would have been the other way around. This is minus 2 omega t. Okay. So if you take power, it is basically negative. Okay, while the current is, if any one of them is negative, it is negative. That's the product. No? So in this case, actually, this is negative, current is negative, and voltage is positive. So outcome here is negative. Okay. Second half, that is second quarter, we can split into 4 quarters of the cycle. Okay. In the second quarter of the cycle, you can see both current and voltage are positive. Okay. And hence the power also is positive. So this is the power. And here you can see again voltage is negative and current is positive. So one of them is negative and hence the outcome is negative. Here you can again see that both are negative, hence this is positive. However, if you look at this, the variation of power, okay, is not actually varying with the same frequency as that of the voltage or current. It is double the frequency. You can see the number of cycles that happen. In one cycle, you have 2 cycles of the power, so double the frequency. And you can also see that the overall complete power, that average power, if you want to see over the whole cycle, if you see. So if I want to calculate the average power, that will be equal to V into I into, okay, sine 2 omega t. What is the average of any sine function over the full cycle? Okay. So positive equal to the negative, so it will become 0. So average power consumed is actually 0. A pure inductor never consumes power on an average. So you can very clearly see here, while it is in during this time, it consumes power, and during the negative part, it supplies back the power back to the source. So that is how whatever the amount it has taken, same amount it will supply it back. So that is how it actually has 0 power consumption. Overall, if you have a pure inductor, which is never the case, you can never have, there will be some resistance which will actually consume power. But ideally, a pure inductor does not consume any power. Okay. So that is the analysis of a pure inductor. So what we understood by a pure inductor, there are basically 2 or 3 important things that you have to remember. In a pure inductor, okay, the current and voltage are never in phase. Okay. Current is lagging by 90 degrees from the voltage. That is the first point that you have to understand. Second point is that the inductance, okay, gives rise to what we call reactance. Okay, so the reactance, what we call XL, is actually equal to omega L or 2 pi FL. Is a kind of it opposes the change in current, which means with higher frequency means more reactance. And also we learned that the power consumed by a pure inductor on an average is 0. It takes power and gives back power. So these are the main important, and power cycling happens at double the frequency of the normal. If there are 50 hertz, it will happen at 100 hertz. Okay. So this is basically the understanding. So what we will do is we will actually do a simple question, okay, and see whether we can answer that with our understanding now. So read the question. A pure inductor is said means there is no resistance. A pure inductor, 25 millihenry, that means L is equal to 25 millihenry, is connected to a source of 220 volts. Okay, so voltage we'll say is 220 volts. Look at this. When I write like this actually means RMS. Okay, find the inductive reactance and RMS current. So I is how much, the inductive reactance XL is how much. There. And they are giving us frequency of 50 hertz. Okay, this is actually looks maybe complicated, but it's an extremely simple question. Okay, so you say XL, you can calculate directly. XL is equal to omega L, which is equal to 2 pi f into L, which is nothing but 2 into pi into 50 into L is how much? 25 millihenry minus 3, okay, 10 millihenry. So this is nothing but 100 pi into 225 is basically nothing but this 100, you will lose 1 0 here, so this will become basically 2.5 into pi comes to around let me tell you the exact value that you need to write down is 7.85 ohms. 7.85 ohms. The ohms, you can see, like resistance unit is. And what is the current? So once it comes to current, we want to calculate the RMS current. We don't deal with anything else other than normal Ohm's law. Is equal to V by, instead of R, we'll say V by XL, which is nothing but 220 by 7.85, which is equal to, we can use the calculator, this will be equal to 28 amps. So this is how you can simply solve using just RMS value. So we didn't even go into writing down these equations, nothing like that. Very straightforward, pure inductor, and we straight away wrote down omega L is equal to XL and solve for current. If you are asked how much is the total power consumed average, if you are asked, what will you say? I square R? No, there is no R. So pure inductor. So average power consumed in a pure inductor is always 0. The answer is 0. Okay. Let's move forward. So let's now look at AC voltage applied to a capacitor. So we have seen resistor, we have seen inductor, we're going to see the capacitor. In the capacitor, actually, again, okay, we can write it through this one is V is equal to Vm sin omega t. We know that. Okay, we're going to write it basically the formula for capacitance. So we say Q is equal to CV, or C is equal to Q by V. So this is basically V, this is C. Okay, so however, we know that okay, dq by dt is nothing but current. So it is C into dV by dt. Both sides I am just differentiating with respect to time. Okay, so which is nothing but C into Vm into d by dt of sin omega t. So this would be equal to C into Vm into sin omega t. If you differentiate, you will get cos omega t into omega, chain rule. So this we can write it as Vm divided by 1 by omega c, or you can say omega c into Vm. So I will write it for a specific reason like it into cos omega t. This is our I. This can be written as Vm by 1 by omega c into cos omega t can be written as sin omega t plus pi by 2. Because sin is positive in the second quadrant. Sin omega t plus pi by 2. So this part, you can see the last time we had Vm divided by omega L. Now we are having here Vm divided by 1 by omega C. So this 1 by omega C is similar to our resistance, in units wise, ohms it is. And this is sine omega t plus pi by 2. That means it is kind of ahead current. Okay. So we can write this as Vm by Xc. So we use the word now. It's also reactance, but it is a capacitive reactance. Xc. The other one was XL, inductive reactance, into sine omega t plus pi by 2. Which means basically what we are saying is that I is equal to Im into sine omega t plus pi by 2, where Im is equal to Vm by Xc, and Xc is nothing but 1 by omega c, or we can write it as 1 by 2 pi f c ohms. So this is our inductive reactance. Inductive reactance, you can see here is see, look at this. Actually speaking, if you had a DC current here, okay, DC source here, and that would have charged this, and after that there would be no more current. Okay, it's like zero current. So zero current actually means, you can see here, if f is 0, that means if f is 0 means denominator is 0, which means xc will become infinite. So it is almost saying that there is an infinite resistance here, reactance here. That means there is no current. That is why in DC there is no current. Whereas if you keep on increasing the frequency, it becomes easier and easier, in the sense that it charges faster and faster and discharges faster and faster, and it will give a lot of current. So F is, the higher the F, lower the XC. Okay, the reactance is nothing but what it opposes. So lower the XC, and when lower XC is lower, naturally the you can see the current is nothing but Vm by Xc, current will be higher. So in the case of a capacitance, what happens is capacitance opposes anything that doesn't change. It accepts things that change. So capacitance is always, it likes changes, change in the current, and hence it produces very less opposition for the current. Whereas inductance always, it doesn't like the change. Whenever there is a change, it opposes more. Okay. So inductive reactance in that way is different from capacitive reactance. Capacitive reactance is always 1 by omega c. Inductive reactance is just omega L. So both of them unit is ohms. Okay. So let's just look at how it looks like in a phasor diagram. So we have V is equal to Vm sin omega t, and I is equal to Im sin omega t plus pi by 2. Okay. So how do they look like? We'll see. Phasor diagram. I am first going to draw anyway V first. This is our Vm sin omega t, nicely, and then we are going to have similarly draw two lines which are the same peaks and draw a circle, and to that circle we are going to draw a radius which is of size Vm, and this height I will call V. Okay, so that is the way V is equal to Vm sin omega t, and we can say the current now. Okay, so what are we saying? Current is equal to omega t plus pi by 2, which means actually in order to for the current to basically align with the voltage, you need to move this to the right by pi by 2. You can say this is 0, this is pi by 2. Move it to the right, then it will align. Okay, so that means it is leading, it is going in the front. So current leads the voltage by 90 degrees. So we are going to draw for the current again the circle, okay, and then its value here, this is our IM, and that is leading 90 degrees in the front, and when they were moving like this, both of them turning around like this, and current is leading the voltage, or we can say voltage is lagging the current. So in the case of an inductor, current lags, and in the case of a capacitor, current leads. Okay, in our phasor diagram, that is the meaning. Okay, so why is that required? When we do a complete analysis of the system of RLC circuits where all of them are there, it's easier for us to deal with it. Okay, so we will show you how to do that in the later sessions. Now in this session we are going to basically conclude by doing a power analysis for this ultimately. Okay, what is the power analysis? So if you look at basically power is V into I as usual. Okay, so we're going to write down here power is equal to V into I means V M I M into sine omega t sine omega t plus pi by 2. Okay, so this is basically Vm into Im by 2 into 2 sine omega t cos omega t, which is Vm sin m by 2 into sine 2 omega t. Even here, if you see, it is varying with a double the frequency. Okay, if you have the current here and want to find out what the voltage is, for power is equal to average power again here is nothing but it gets to become 0. Average power becomes Vm Im by 2 into sine 2 omega t. Sine 2 omega t, if you take it, it becomes 0. So how do we draw the picture of both of them? So if you see, it should be actually like this. So you can see that both are positive here, and hence this is positive. One of them negative, so this is negative. So here both are positive in this, again this is positive, like that. Both are negative in this case. Okay, so hence it is positive. So here what we can see here is always that whenever current, this is voltage, this is current is leading here, and this is our power. So here we use the concept again, it gets charged and discharged, and charged in the opposite direction and gets discharged. This is what continuously happens, okay, in the case of a capacitor, and that's why it takes the power again and gives back the power at the rate. See, you look at this, charging and then discharging, and charging in the negative direction and then discharging, again charging in the positive direction, discharging, charging in the negative direction, discharging. So this is what happens continuously in the case of a power consumed by the capacitor, and again it will become a 0 for on an average. A pure capacitor also does not consume power. A pure inductor and pure capacitor does not consume power on average. Always only the resistor consumes power. Okay, it dissipates power in the form of a heat. So let's just look at one or two simple questions, and then we'll go to the next part. So let's say there is a 150 microfarad capacitor and is connected to 220 volts and 50 hertz source. Find the capacitive reactance. Very straightforward. Capacitive reactance Xc is equal to 1 by omega c, which is equal to 1 by 2 pi Fc, which is nothing but 1 by 2 pi into 50 hertz. Okay, into C is 15 to 10 power minus 6. So if you actually calculate this using a if you calculate this using a calculator, you will get this as 212 ohms. So you can do your calculation. Okay, that is basically the point that they have asked. Reactance, capacitive reactance, we have figured out. Okay, now the current RMS and peak both are asked. So current RMS I is equal to generally V by XC, which is nothing but 220 divided by XC is 212. This is 1 point something. So how much is that something? 1.04 amps. This is I. Okay. Now they have also asked us to calculate the peak value, that is I max. Yeah. So we have this formula I is equal to I max by root 2, or I max is equal to I into root 2, which is 1.04 into root 2. Okay, which will come to 1.4 something. Okay, it will come to 1. Let's say 47 volt, 47, 1.47 amps. IM. So the next part they are asking is that if the frequency is doubled, what happens to the capacitive reactance? What happens if the frequency is doubled? If 50 becomes 100, this will become half. If frequency doubled is equal to 100, then XC will become half of that, which is 106. Okay, that is how you can calculate the things in the in the case of capacitive reactance. So that is the capacitive reactance. When current also, current will, what will happen to the current when capacitive reactance actually becomes half? Capacitive reactance becomes half. Okay, so if capacitive reactance becomes half, current gets doubled. So current will become 2.08 amps. So we have answered all the questions in this question. Okay. So this is not, it's a very straightforward thing, like almost like resistance only. Once we understand this, it is like a very simple questions. So initially you may get a little awkward with this, what is this RMS and all that, but gradually you will get used to the question. So the second question is a light bulb and an open coil inductor, okay, are connected to an AC source through a key as shown. Now the switch is closed, and after some time an iron rod is inserted into the interior of the inductor. So the glow of the light bulb, what happens? Increases, decreases, unchanged as the iron rod is inserted. Give your answer and give reasons. So what we have done is we just connected an inductor and a bulb, okay, and a switch here. So when you switch it on, okay, the light comes on. Okay. Now what we are going to do is we say it's a wire like this wound around nothing, okay, in the air. Now I'll take iron rod and insert through that. What will happen to bulb? That is the question. Whether light will become brightened or it will become dim. What will happen? Think about it. Okay. So if you see here, whenever you, what happens when you actually do the inductor? When you in the inductor, if whenever you insert iron rod, you are actually increasing its inductance. Okay, if you are increasing its inductance, the inductive reactance is also increasing. This L will increase. If the L increases, means inductive reactance increases. So if the inductive reactance increases, then what will happen? So here there is already a resistance there. Okay, so the lamp has a certain resistance and some current is flowing through it, it's light up. So inductive reactance increases. This is an AC, so inductive reactance increases. So there is more voltage drop that happens in this, because the whatever the voltage that you are giving here, it is split between these two. So more voltage drop happens here and less voltage drop happens here. So which means basically current through this will be less and it will become dim. So that is basically how you can analyze this circuit. But for a more quantitative approach of how much it increases and all, we will learn RLC circuits. When we put R, L and C together, what will happen? When we analyze that, we're going to get a better understanding of how to compute this. Okay, so till then, enjoy.